Good morning, everyone. So yeah, I am Bhavesh, and I'll be presenting a workshop on diffusion models today. So let me just share my screen. Let me know once it's visible. Okay. Okay. So yeah, so this workshop is basically going to be an introduction to diffusion models and everything, and specifically stable diffusion. We'll be doing a bit of stable diffusion today. So we'll start by just having a basic introduction on what are we actually like, what is it like diffusion model if you're not familiar with the base. We'll go through walk through a simple approach to diffusion, first principles approach, and then we'll look at denoising diffusion probabilistic model. This is a paper which is one of the like foundational papers of diffusion models, or at least modern diffusion models. This is like the first paper of that, and then we look at the stable diffusion paper, and then implement the inference pipeline for stable diffusion from scratch. So yeah, so chances are that if you're already aware of existence of of diffusion models, because they have been the talk of the town for the past few months, right? So stable diffusion, Dall-E from OpenAI, MidJourney, all the AI art generators are basically were like trending a lot in all the social medias, right? So all of these, most in fact, like most all of these AI algorithms are basically powered by something called a diffusion model. And diffusion model have basically like changed the entire generative AI landscape in both video as well as image. So today we're going to look at images, but soon after the image trend, video also came out with make a video and image and video and so on. So, so what is the speciality of these generative diffusion models that that have recently released? Are basically that they are conditioned on text. So you can write a text prompt and basically get an image from that text prompt. And then there are also other stuff like image to image. So the community has built many extensions like
Bhavesh,
they,
Bhavesh, sorry,
yeah,
Krishna here. In
yeah.
fact, I have not come across diffusion model earlier. Can you please give summary of that? What
We'll
exactly
go
it?
over that
Why
anyway.
that
So
model is? What does it do?
we'll anyway go over that right in the future.
Okay,
This is the
okay,
workshop on that only. So
right,
yeah,
right.
it's yeah. So yeah, so basically they have so basically the task that we are essentially solving with diffusion models are things like text to image. So taking a text prompt or a text caption and generating an image out of it. Uh, Taking an existing image and basically adding a text prompt on top of that, and then turning that image into something. Let's say you have a drawing of a tree. You put a text prompt as draw a tree or something like that. Then it will turn that into a realistic looking tree or something. And you can also edit images, so you can change people, remove people from the images. And let's say there's a bench on your thing which is very rusty, you can edit it out and make it uh, without rust. Like you can edit and tell it that remove the rust from this chair or things like that. So you can do a lot of things with this, and the community, AI community, has basically done a lot of extensions to all these models. So some text to image examples that I was able to generate from my local computer using MidJourney, Stable Diffusion, and all this. So it's like a mixture of these. Some of these that you're seeing on the screen. So I think this was Dall-E. What's it? So, yeah, I think this was Dall-E. This was MidJourney. This was Stable Diffusion. Stable Diffusion. I think this is Dall-E again, and then Stable Diffusion, Stable Diffusion, Stable Diffusion, MidJourney, and MidJourney. Slightly. No, I think this is Dall-E. But yeah, anyway, the point being that these are some examples. So, so we are going to basically do something along these lines. We'll be by the end of this workshop, we'll actually be able to generate some images like these. So, what are diffusion models? So, for those who don't, so like obviously this workshop is on diffusion models, so we'll learn about that. So the basic idea behind diffusion models is similar to that of an iterative of a denoising autoencoder. So everyone's an autoencoder, right? You have an encoder, you have a decoder, and then you put some image through it, and then you get some output through it. And in the middle, you compress it to a lower latent vector representation. So denoising autoencoders are when you send in a noisy image and make and train it in such a way such that the prediction is a denoised image, like without the noise, like the original image without the random noise. So diffusion models are essentially that they are denoising autoencoders. So the idea is that you start with a completely random image of a noise. Just to make sure we are clear, now we'll be looking at normal diffusion models, so not stable diffusion or any of those text to image models, just pure unconditional diffusion models, which just generate images, random images like cans and all. So I just wanted to put that over there. So yeah, anyway. So the process basically begins with completely random noise. And what we do is we do a bunch of processes. The basic idea being that we train a neural network such that it iteratively, like not in a single shot, but iteratively removes a bit of noise slowly in a loop and multiple steps until you get like a very high quality, clear image of your of the clear image, basically based on your data set. So based on the data, let's say you trained a data set on faces, a diffusion model will always give you different random faces uh, when you use it. So the idea, the aim of this model here is to basically remove the noise from this, uh, remove the noise iteratively. So it removes the noise, and then it again takes this image and then removes the noise from there, and so on and so on. So basically the idea is that small changes are made at each step. So even if there are errors in removal of noise or anything, it can always be fixed up in the next step and so on. So you're not doing a complete like complete one shot thing. So you can't just take this random noise and then directly predict this. That would be insane, right? But that's not possible, at least now, at least today it's not possible. But you iteratively go on and remove noise little by little, so that you, let's say you start getting some structure, and then you slowly remove make that structure more refined and everything, and at every step you're making the image more refined and more detailed and high quality in general. So this is like the general gist. We'll look at how everything like works in detail. So let's take a very simple approach. So in this simple approach, we'll be basically building a diffusion model, as a thought experiment, and we will be looking at it from a first principles perspective. It will be very basic, just for our theoretical understanding of what diffusion models are. So the first thing is that we'll start with a unit. So this is going to be like our autoencoder architecture in the way you can think of it. So we'll put in an image and you'll get an output. So in general, if you're not familiar with the units are popularly used in semantic segmentation tasks where, let's say you have a chest medical X-ray or something, and you want to segment out the parts which are problematic or which have pneumonia or something like that. So UNet was basically used for that. It's like an image-to-image model. It will take an image, downsample it, compress it to a latent representation, and then upsample it back to the original, to the same image of the same size, but with like modifications to it. Let's say like a segmentation map or something like that. So this is a basic unit, nothing special. But the difference here from a regular unit is like normal autoencoders or anything is that unit has basically skip connections to its uh, corresponding decoder side. So a regular autoencoder doesn't have skip connections, right? But a unit would have skip connections. So that is an extra thing. So it's basically a bunch of ResNet blocks, like under the hood. So yeah. So we are going to take a basic unit. And we are going to create a denoising autoencoder from that. So we'll have our unit here, and then we have some input data. So this is some images from the fashion MNES dataset. So we take these images. So these are like 28 by 28 pixels, I think, in width and height. And what we do is, what we are going to do is we are going to train a denoising autoencoder, right? So a denoising autoencoder's goal is to take some image, add some random noise to it, and then decode it, and then basically remove the noise and make it and turn it into the original image. So that's our goal. So no diffusion model stuff or anything, just a regular simple denoising autoencoder. Yeah, that's what we are going with right now. So we just corrupt the data. So we add the noise in varying amounts. So let's say this image has a little bit of noise, this image has like the most amount of noise, and it's like barely understandable. Like no, like it's like literally you cannot understand what's in the picture, right? It's like a full of noise image. So yeah, so we'll first corrupt the data, and then we put it through the unit, and then our model, we train the model in such a way such that we basically get the original image back as prediction. So you can say these are like slumps. Let's say the last image, which was like fully noisy, it's just, the prediction is just a blob, right? Because it's really difficult to predict anything specific from this amount of noise. But nonetheless, we basically trained a denoising autoencoder, and we have our network predictions here. If you have any questions so far or anything you want me to repeat, you can let me know.
Okay, so Bhavesh, in this example, that rightmost one, it can't come to the original one. You're saying this is the best,
Yeah,
like, to predict.
yeah. This is the best that we can do, right? Because like it's just a one-step process, right? You just take this noise and then it's like a very noisy image, like too much noise image. So that's
Oh,
why
so
it's not
here
possible
there is
for the
no
model.
iterations. It's a one step
Yeah,
only.
we are not talking about diffusion or anything right now. We're just talking
Okay.
about denoising autoencoders, simple denoising autoencoders. Yeah. So no diffusion, anything. We'll talk about it like iteratively. We'll add the complexity to this to basically turn it into a diffusion model. Right. So yeah, so these are our predicted images. So there's no diffusion or anything. So now there are a few issues, right? Like obviously I just told you, like one is that images which had a lot of noise, the predictions are not that great. It's just a blob, let's say, in the rightmost thing. This at least some has some structure, but it's still obviously not the most clear image or anything. So our goal of diffusion is to start from complete noise and denoise it completely, right? So our actual goal would actually have like complete random noise, right? As I told you, as I showed you in here, like we start with completely random noise and then image. So a simple denoising autoencoder doesn't seem to do the job. We had a complete noise, almost complete noise, and it didn't do our job. So that's an issue, right? So these are the two issues that we need to solve. So okay, so we'll not solve it anything in the training or anything, but what we can do is we can use a few up tricks up our sleeve to basically generate better, like instead of these blobs, generate better images. So let's try that. So we'll do something called sampling. So we trained our denoising autoencoder, no diffusion or anything, just a simple denoising autoencoder, okay? So, and now what we'll do is we'll do something called sampling, or which is basically doing something at inference time. So we have trained our model. This is our pre-trained model, and we'll be performing inference to generate good images. So because our predictions at high noise levels aren't so good, what can we do, right? So okay, so we'll basically start with some random noise. So this is the first random noise, like it's completely noisy. There's no structure or anything visible in the image or anything. It's like pure noise. And then look at the predictions. And okay, and for this particular random noise, it is predicting a shoe. It could be anything, right? It's completely random. It could be a shoe, it could be a cloth, it could be a pant or a shirt or anything. But it chose to do a shoe, but it's still obviously very blurry and everything, right? So what we can do is, so instead, okay, so before we move on, so generally we have our original noise, our original input was very noisy, right? And our prediction was this much. So what we can do is we can modify our original input, that is this thing, and move it only a bit towards the prediction. Let's say 20%. So our prediction is this, right? So we modify this input such that this part, this structure that we are showing in the shoe, right, is slightly visible in this random noise. So basically we are moving towards the prediction, but not at the full speed. Like we are not doing one step, full one shot. What we'll be doing is we'll take this noisy image and take some mix factor, let's say, and let's say 20%. So 80%, we'll keep 80% of the image, and remaining 20% we'll add this image, and basically we'll add both of these to basically get a new noise, which is basically less noisy than the previous one. Like generally you can't see, but it's like you can see like some aspect of the shape here of the shoe. But basically we only add let's say a very small percentage of the or prediction to the original input. So we're just modifying the original input right now. We are not using the predictions to do anything. We are using the predictions something like a goal sort of thing that you have to move towards, but in a much more iterative manner. So we do that, and then we take that as input in the next step. So we are basically again going to sample an image from this random noise, but which is an improved random noise. It's like a better version of the original random noise because this has some bit of structure in its prediction. And then we put through it. And then if you see, now this prediction is a bit better than the previous one, right? Our previous shoe was highly blurry. Now, when we did this process, our shoe is like a little bit less blurry. So we get a less noisy version. So now our prediction is a bit better, right? Instead of the direct one-shot thing, if we just slightly move towards. Now we'll do this again repeatedly multiple times. So we'll take this shoe, add 20% of this image to the previous thing, and basically now we can see the structure is forming in the noise as our input. Now we put it again through the unit. Now we give it a much clearer image, and then we go do it repeatedly multiple times. So and finally, until k steps, it could be 100,000 whatever steps that we defined. And finally, we'll basically get a final prediction, which is much better than what we would have gotten from a purely random noise. Yeah, I think
Yeah,
someone
I
has a
have
question.
one question is why not use the whole output itself as an input in the next step instead of mixing?
Yeah. So yeah, we can do that as well. So the idea was to talk about like how we can move from noise. So that's a proper diffusion process, but like this is like a very simple and basic approach that I'm talking about. This is one approach. You can obviously do that as well. So there are anything that you can do. This is just an example to show you that how you can iteratively remove noise from a noisy image. So it's just to show the removal of the noise process. We are modifying the original input. But of course, you can use this prediction as well as the input and then repeatedly go there. But because that wouldn't actually show us the noise removal process, right? You can see the original image is getting less and less noisy just to show you from a theoretical perspective. That's the reason we are doing it this way. But otherwise, it's not any proper definition or anything of diffusion or anything. It's just an example to give you an idea of what the target or objective of a diffusion is, to iteratively remove noise from the input.
Okay, thank you.
Yeah. So basically, as a summary, in what we did our sampling was we some random noise. We looked at the model prediction and only moved, let's say, a little bit towards the prediction, and feed the slightly less noisy image back into the model and get a new prediction, repeated a few times, and then we finally get our output. So the model pairs a denoise image even at the first step, right? Like we could have still used that as the input, but we are only moving a small way up there. And over multiple steps, our input basically gets more refined, and we are like able to see like simulate at least a process of removal of noise bit by bit. Right. So this is sampling. Sampling is basically done at inference time. We're not training the model or anything. Here we are just doing, we are using an existing trained model, a denoised autoencoder, and using some tricks to basically get better images instead of in multiple steps instead of a single step. So this was like a basic, simple approach. If anyone has any questions, like in there to get some idea or anything, they can. But otherwise, this is like the general idea behind it, just like a theoretical idea. It's not anything that you would use in production or anything. This is just to basically get the ball rolling.
So autoencoders and GANs were the original generative tech. And now we are moving towards a new tech, I guess, called diffusion model.
Yeah.
But they do build
Diffusions.
on,
They do build on autoencoders.
do they also inspire from GANs, adversarial training?
Well, not exactly though. No, not exactly. But some components of it in stable diffusion that we will see forward will actually have some aspects of GAN.
Okay.
Although the original stable diffusion kind of didn't use the GAN version and used the variation autoencoder version, but we'll still talk about it nonetheless. Yeah, anyone has any other questions?
So
doing
Bhavesh,
some.
whatever we have seen just this is only autoencoder model, or this is a diffusion model?
This is not diffusion or anything, just a general denoising autoencoder, and we are
Yes.
using some tricks of diffusion to basically get a better image instead of,
Okay.
because normal denoising autoencoder do one step. We are using some aspects of diffusion. Like again, the sampling is just it's like a very high level process.
Yeah.
Specific to diffusion models, there are multiple ways to do it, like n number of ways, and there's no best way right till now, in fact. And we'll actually look at
And
all
here
the.
also you are taking, like in this example, 20%. Maybe the learning is
Hmm.
better is instead of taking one full image, as somebody said,
Hmm.
if you take
Hmm.
20% the mixed image, each time 80% of this, 20% of that, or any
Hmm.
combination. Maybe the learning
Hmm.
is more in each iteration. Is that the logic
Huh.
behind?
Uh, like that's what, like that could also happen, but at a very small example like this, it doesn't really matter though, because it's a very
Okay.
simple example, right? Fashion image. So,
Okay.
but at larger images, things could be different. But for smaller images, at least when I tried it, didn't really make that big of a difference or anything.
So now this model finally, uh,
Hmm.
now say you pass this image, original image, it is supposed to give you the maybe shoe in this example, the denoised
Hmm.
image. But
Hmm.
does it work in any other image where the noise could be different kind of noise?
Yeah. So this is like a random unconditional generation, right? So we are not conditioning it to only generate shoe or anything. The fashion MNIST has what clothes, they like pants and t-shirts and dresses or shirts and these sort of things, right? So with any random noise, every time it will generate something different. Sometimes it will generate shoes, sometimes it might generate pants, sometimes it might generate anything. So it will be like completely random. The target at least,
Okay,
because this is unconditional generation.
okay, okay,
They're not putting a condition on what to generate. It's just generate something just randomly.
okay, okay.
Like GANs, like if a GAN's trained on faces, it would generate basically random faces, right? You don't
Mhm,
usually condition it. Like the pure GANs are always usually non-conditional only.
mhm. So that way, the model which is trained on any image, say shoe image, it can work in for a
Hmm.
face image also. That's what we are saying.
Uh,
Because the noise
no,
is
no, no, not exactly. It should be in the data set. It will work on any class in the data set,
in the
not
data set.
any random
Okay,
image in the
I see.
data set from the data set.
Mhm. Okay, okay, got it.
Yeah.
Yeah, thanks. So that way, suppose somebody is using the say face authentication model, the
Hmm.
face may not be clear all the time, right? So
Yeah.
whatever the phone captures, so they can first
Hmm.
denoise the
Yeah. Yeah.
face and
Yes.
then actually use a maybe face matching model.
Yes, they
Is that
can.
a use
Yes.
case?
Yeah, that's a really good use case. Yeah.
Okay, okay, got it. Thanks. Yeah.
So yeah, so this was a simple approach. Now we'll actually look at the base paper of diffusion models. Like this is like the first, like their diffusion models at least have been theorized a bit before also, but this is like the at least in modern diffusion models, this is like the first paper or like the base paper from which everything is built on top. So it's called DDPM or denoising diffusion probabilistic models. So this will basically be a more sophisticated. It's like it will be similar to our previous approach, but it will be a bit different. So now we'll actually be also training the model to actually remove noise. There it was like we were training the model to do it in one shot, right? To get the full image in one shot. Here we'll actually take a more uh, step-by-step approach sort of thing in training, and then do the sampling in a similar way, or like the at inference time. So our original simple approach was predicting a fully denoised image, right? We take some random noise or little or a noisy image, and then we predict a fully denoised image. The objective in DDPM is different. Here, instead, our goal is to predict the amount of noise that was added, and like iteratively remove that noise at inference time with the same sampling method. So, like we'll just use it in a different way, but the idea of sampling is basically to remove noise in some multi-step way, right? So it could be anything. In our case, we'll be basically removing noise. So our model won't predict the image, but rather predict the actual noise that was added to that image to basically generate that image. So that's the idea. We'll go through it a bit, but yeah. So
So
the main components, yeah.
sorry, so once you predict the actual noise, so the idea is to remove that noise from that
Yeah,
input
so
image.
you minus it from the
Okay,
original image or whatever and
okay,
remove that noise. and then you feed the output of that back to the as input, as someone has said, right? So in the previous thing, that why can't we? So in this case, actually the output is used as the input in the next step.
Okay. Thanks.
Yeah. So the main components of this setup are basically a scheduler, a model, training, and inference. So again, we are going to go through an intuitive explanation. So in general, there's a lot of math behind everything and decision thing, and I'll link to references at the end, if you want to learn in like very technical depth. But the idea is that because like there's not enough time in single workshop to cover everything, but a scheduler is basically a system or an algorithm which will basically add noise to the image. So now there are multiple ways to add noise to the image and multiple ways to remove noise. So the scheduler's job is to add the noise, and also when the noise is being predicted from the model, use that noise to remove it. So it doesn't just do a simple addition or subtraction. There is a process to it. So DDPM has a specific scheduler. We'll talk about that in the next slide. But yeah, apart from that, we have a model. We have a unit model, but it has some more improvements over the basic unit that we saw before, and then training and inference. Yeah. Yeah.
One question, Bhavesh, very
Yeah.
basic one. So why do we add noise, or why do we remove noise? What is the I mean, basically fundamental idea behind it?
So the idea is that we want to generate images or whatever, right, from nothing. So from nothing means in this particular case, random noise is a random image, or random noise is basically nothing, right? So if you just do random normal distribution and get a vector, it will be noise, right? Random noise. It won't really make sense or have any image properties or anything. So the idea is that we take that as our nothing or our starting point, and then we use some techniques such that we can actually turn that noise into a full image, like a full proper image with details and everything. So like in order to turn something from nothing, you just you need to have some raw ingredient, right? So that raw ingredient in this case is the random noise.
Okay, so we don't use any previous images or any previous
Yeah.
inputs.
So like in a normal autoencoder, you would use some image as an input and then encode it and then again decode it to reconstruct the original image, right? But in
Right.
diffusion models, the goal is to start from like pure noise and turn it into something like which is like a proper image.
Okay, I was wondering that how these images are basically combined with different image ideas, right? So, but as per your explanation, that we are creating basically from nothing.
Yeah.
Okay, that's
And
interesting.
they'll actually a lot of like when we do the implementation part, you'll actually find a lot of things of that nothing part. So we'll have seeds and all random seeds and everything that basically determine our entire process of generation, like what
Got
we
it.
are going to build.
Got it. Thank you.
Yeah. And a follow-up question. So when you say here you are removing the noise, you are removing through model, right? The trained
Yeah,
model.
through the model. Yeah, through the trained model. So now we are not using a denoising autoencoder. Now we'll actually go to the diffusion model and basically do our thing. Yeah. So yeah, before we talk about the scheduler, we'll just talk about the improved unit that is in this case. So it basically has a bunch of improvements. It has things like dropout layers for better training. It has group norm for group normalization. It has multiple ResNet layers per block. So it has multiple blocks, right? And it has more number of layers. And especially it has attention in it. So it has spatial attention, at least the normal DDPM. When we look at stable diffusion, it will have a much more sophisticated cross attention. But yeah, it has the attention built into it, but only at the lower resolution blocks, so not at the higher. So once you get closer to the embeddings or the latent space, you will have more attention layers on there. And then there's also something called conditioning on the time step, and we'll actually look at that when we look at the training process. But the general idea is that removing noise. Now our goal is to iteratively remove noise, right? So there needs to be some information on how much noise to remove, right? That how much noise is basically being our time step. So when we add noise, let's say we add in 100 steps, we will know at what point we added how much amount of noise, right? So we are basically going to train our model to basically take that information. Let's say in this particular input image, I added this input image was at time step 350. So I'll give that noisy image to the model, and also the time step that is 350 to the model, and tell that this image was obtained from pure noise at time step 350, and it will use, and theory is that it will use that information as well to remove the uh, proper amount of noise. So not just randomly any amount of noise, but we have to like properly remove how much amount of noise that is needed, right? So we are yeah. So once again, I think and get okay. So for a second here, let's assume that so for a second here, let's assume that this is all shoe. Okay, this is all whatever the shoe is. So all these, so this is a cloth, right? Just imagine this is a shoe. And we have this shoe image, so the same shoe image, and we are gradually adding noise to it, okay, to create like a data set or something. Okay, so this is all shoes, shoe or whatever, shoe and shoe, but like these are all shoes, but these were added. Like let's say this is at timestamp 5, this is at timestamp 10, 15, 20, 25, 30, 35, 40. Okay, so this will be till 40. So in 40 steps, we basically added gradual noise to it using our scheduler. Okay, so we added our noise. Now what our model will do is, let's say we'll take this image. Okay, at time step 20, our image was from this to this, and we'll tell the model that take this image and take this information that this was at time step 20 and predict how much noise was added. So now we are trying to predict how much noise was added at time step 50, let's say 19 to 20. So from t minus 1 to t minus 2, how much noise was added to it, or essentially, so at least like at least the basic idea is that we are trying to predict. We are basically trying to reverse the process. So this process of adding noise is called forward diffusion. So this is called forward diffusion. And our model, what it is trying to actually achieve is actually reverse this process and achieve backward diffusion. So we diffused noise into the image, we added noise into the image, and now our model will basically take the image and this time step value to basically try to reverse the process and predict how much noise was added. So it is actually trying to jump to the original image from any step. So our goal is that now during training process, we are not going to allow it, like we are not going to train it to go from all the way from pure noise to that to the original image. We are not going to train it in that way, but rather we'll like train it in batches. So it will just randomly put some images, say that this is time step 5, and then basically try to predict the noise that was added to it. Like when we go to a training process a bit more, we'll get I guess you'll get that. But the basic idea is that we'll send some images and we are trying to basically predict at that timestamp how much noise was added from the original. So like general 19 to 20 is like just an example. But what I will actually do, we'll actually calculate how much noise was added from time step 0 to 20 or something. But again, that depends on the scheduler structure though. But the idea is that we basically want to predict how much noise is added from the previous image to the current image or whatever. And overall, when we do it at inference time, we'll actually be doing it in a step-by-step way and reverse this entire process to finally get the original image.
So here, when you give the model the input, along with the noise image, you have to give the timestamp also as input.
Yeah. Yes.
But in practice, how will you know the timestamp? Say
No. Yeah. That is just to train it so that we can train it in different. So sometimes it will have images with time step 5, sometimes with 40. So it will basically know how more noisy and less noisy things works and all, just to train. During sampling, then we'll actually go from 0. We'll start from 0, we'll go to 1 and 2. Again, this timestamp will be like in reverse process only. I just named it 5 to 10, but I think in practice, it's like your most noised image is 0 and your least noise image is like 1000 or whatever.
Right. So my question is, say during sampling, so you are actually synthetically noising, so you know the time, you know the timestamp also, how much noise is added at which timestamp. So so your final model will expect the timestamp also as one input along with the image.
Yes,
right?
yes.
So
So
how will
timestamp will be just normal. So let's say we are trying to predict an image in 1000 steps. So we'll just normally iteratively go from 0 all the way to 1000. Now our model has arbitrarily learned to remove noise from at any given timestamp, right? So when
Right.
we go iteratively from 0 to 1000, 100 or 1000, whatever, we
Uh-huh.
will actually start from completely random noise like this and end up at complete and a clear image of the shoe like this or whatever.
Okay.
So our model is basically trained in that way that given whatever timestamp, you have to just spread the noise. Now we'll just do it iteratively in a sequential manner, and that will basically allow us to generate the full image.
Let's say in this example, 0 to 1000. So maybe at 700 timestamp itself, the clear image would have been obtained.
Yeah, that's
We
fine.
have to
Like
necessarily
if
go to
you
700 to 1000. So how do we know when to stop that?
you don't actually stop it. You just let it go till 1000 if you want, like
Okay.
because it's like it's up to you because you set the number of time steps you want to go over it, right?
So, but when you go beyond 700, say, assuming 700 is a step where clear image comes, it won't deteriorate the image when you go beyond
Uh, well, it
700.
depends on the model. Sometimes it can change, sometimes it cannot. For simple example like this, it won't. But like if you go to actual real world images, things will change.
Okay.
I will actually when we do the practical thing, like we can experiment that. We'll change the time step from 1 to 1, and we'll see. But this is basically the training timestamp. Let's say in DDPM, the number of training timestamps, let's say, were 1000. So it was able to go up to 1000, but it's not necessary that we always have to go till 1000 to generate our final image. We can let's say we can get our final image in 0 to 50. We can experiment depending on what the model is. In Stable Diffusion, 50 is the usual number for going to the timestamp, but you can go to n number.
Okay.
But like even if you go beyond the number it was trained for after training, it can maybe still extrapolate. But in general, you set like a very high number in the training process so that you can go from any arbitrary timestamp, like any sufficiently arbitrary timestamp.
Okay. Okay. Thanks.
So yeah, to summarize, basically, the forward process is called basically forward diffusion. So we gradually add noise, and then what our model is trying to basically reverse this process of addition of noise by removing noise iteratively. So that's our goal essentially. So let's go back to our original thing. Yeah, so that was the goal behind conditioning on the timestamp. And then we have some downtime. We have something else with parameters that are learnable. So yeah, so there's some general architecture improvements, but the other things are like the main things are like this attention and the conditioning of the time step. So yeah, so that was a unit. So now we'll actually look at the scheduler of how of what it does is. So our training plans, because it's as we talked about, is our forward diffusion process would basically involve addition of noise. So we have to also remove the noise iteratively during inference. So we need something which can do this in a controlled way and schedule the noise, because like at every timestamp we have to remove some amount of noise, right? So that we can have many different ways. So there are many different kinds of schedulers. Some like KLMS, Euler A, DD, MNS, and there are lots of bunch of schedulers. And all of these are like you can train on one scheduler and you can do inference at using another scheduler. That's also fine. So that's the way it's like. Scheduler is like a modular block which you can plug and play depending on what works best. So there's no best scheduler or worst scheduler. It's just they are schedulers. Also, this diffusion models is a very new area of research, right? So there are no hard and set rules on what is the best way or what is the worst way to do things. So it's just people have tried a bunch of different things, and there are a bunch of different ways to do the same thing. Yeah. So during the forward diffusion process, so how much noise is added at different time step is basically determined by our something called the noise schedule. So yeah, so that a scheduler will basically create a noise schedule and add different amount of noise at different times. So our scheduler's job is we give it an image. So we give it an image and we give it a timestamp t, and it will basically give us a noised version depending on the timestamp. That's our end goal that we want to achieve. So the DDPM basically adds a small amount of noise at every time step. So for any, let's say, given time step t-1, let's say you are at time step 30 and you want to predict a more slightly noised version 31, so xt. So the way we are going to do is we are actually going to use the use this particular term as our mean in the normal distribution, and this particular term as our variance. So basically, okay, so before we go over this math, I think it's just very basic. It just looks maybe a bit scary or whatever, but the general thing is we are going to add noise from a Gaussian distribution. Gaussian distribution basically a normal distribution, right, which is basically a bell curve which has some mean. A normal distribution is basically a Gaussian distribution with mean as 0 and variance as 1. So -1 and 1. So this is like a normal distribution, but if you have different means or different variances, then it's basically Gaussian. So Gaussian is like the parent or whatever. So our Gaussian distribution is basically has some mean and some variance, and we want to add some noise sampled from a Gaussian distribution. So we have in general our PyTorch normally in PyTorch or TensorFlow or whatever, when we do or NumPy even, when we randomly sample some value between 0 and 1, right? It's usually from a normal distribution, or if you don't specify the mean or variance, but if you do specify that, then it's like from a Gaussian distribution. So that, like in implementation, right, that's like the default way. You always basically there are more chances that your values will be closer to the mean and less chances that your values will be closer to the deviation. Yeah. So basically, in our in this paper, what they basically did is, so let's just forget about this. We'll just do is that our new xt value is basically equal to square root of 1 minus beta, the previous image, so that is xt minus 1, and added with square root of beta multiplied by a noise which is sampled from a normal distribution. So this is a normal. So we sample some random noise from a normal distribution which has mean 0 and variance as 1, and then basically scale it with this term, which is root of beta, and we add it to the previous time step noise image, which is again scaled using root of 1 minus beta. Right. So if you think about it a bit, it's a bit similar to our original thing. Like intuitively, it's a bit similar to our original approach to removal of noise thing, I think.
Yeah, is the average of the previous time step plus the noise.
Yeah. So here, if we just add a root here and basically add a root again here, and then instead of this, we add a normal distribution noise, then this basically becomes that. So we are just adding, let's say, 80% of the original image with 20% of the noise. So in our simple approach, the prediction image was acting as the noise actually. But in here, we'll actually have real noise, not the prediction, but have real noise, and basically use some percent of that is the root, and then add it to the 1 minus root of the 80% of the remaining image or whatever. So it's basically we have 100% image. Now we are only taking like 80% of that and adding 20% of the noise. So it's essentially like intuitively it's doing that.
The square root is not clear. Otherwise, average formula.
Yeah. So it's just that they did it that way. It's like it's not a specific thing. It's just their formula for their scheduler. So there are many different schedulers. This is one scheduler that they used. Okay. Now, yeah. So, but here now let's just talk about what this beta term is. This beta term is basically, you can think of it like a learning rate schedule. It's actually called the variance schedule, and it can be like a linear or quadratic or cosine function or anything, which basically determines how much noise is added per time step. So you can so we have learning rate schedulers, right? So our learning rate schedulers sometimes are linear. So you sometimes like linearly reduce the learning rate. Sometimes you have a step learning rate, which will always reduce it by twice. And then you'll have like say a cosine function as a learning rate schedule. So there are different ways. So similar to that, you can have a variance schedule, which can be of any function. So that beta t will basically determine it. Now there are two problems with this. There's one main problem with this. That is that xt is basically dependent on xt minus 1, right? So if you want to get xt, you need to get xt minus 1. Now, as I said in training, we are not going to train it to go through the entire backward diffusion or forward diffusion process. We'll just randomly take some images, add some random noise at different time steps, and ask it to predict what was the previous time step or whatever. So let's say we want to calculate x at time step 500, we would have to, because it is t-1, we'll have to actually know x499. So if we want to know x499, we'll need to know x498, and so on all the way to 0. So we need to calculate, we have to run this scheduler for 500 times just to get x500 noise at time step 500. So our goal is to basically create a scheduler in such a way such that we can get any arbitrary time step given the original noise or the original image, basically our original proper image of a shoe or whatever, at any different noise time step we want to get, because we're doing forward diffusion, right? We are adding noise. So adding noise is like we have a shoe and we want to get a different shoe at any different time step. So we can basically reformulate the original formula into something like this, which is basically the same as that, except that now we have removed the root. So we have just 1 minus, okay, sorry, not remove the root, sorry. We have modified the function. Yeah. So we had this, right? So now what we're doing is, now we take this thing, we remove this. So we remove this part, or at least specifically this part. We specifically removed the part under the root and replaced it with alpha t. So yeah, so alpha t replaced it, and then not exactly replaced it though, but we have also something called alpha bar t, which is basically a product sum of multiple time steps. Like we have a schedule, right? So this is like a schedule, let's say a time step schedule. So we have 0, 1, 2, or whatever. So this entire thing will go like this. So we have an entire schedule, right? So at any arbitrary time step, we can basically get like we can basically calculate this entire thing because we already know the schedule. Let's say if it's a cosine function, we already know, we can always calculate cosine directly, right? So that sort of thing. So we get that, and we basically do two things. So one is, yeah, so this part is basically replaced by alpha t square bar, and the variance part is replaced by this. So now here what we actually have is, instead of this, we have root of alpha t bar t, and then instead of this, we have 1 minus alpha t. So this is just some mathematical tricks that they have done to essentially what do is that he given, and as you can see in the formula, this thing is actually reduced to t0 actually. So not t-1, but rather just 0 actually, not even t0, just 0. So now to get basically to get a noisy image at any random time step, we just need the input of the original image, not like we don't need to calculate the previous time step or anything. We can directly get any arbit. So this makes our process a lot. Sure, we can still use this, but for obviously it won't be scalable, right? Because it will be like slower. So it's just a faster variation of that same thing only. Again, it will still use beta and everything. Beta is still our main thing. It's just that we have added some extra terms to encapsulate beta into something else.
Rohit, I missed the point how you went from xt-1 to xt, and now from x0 itself, you are going directly to xt.
Yeah, so basically they reformulated it. They basically turned this original formula. They added some terms. So they basically added some terms to basically replace that. So now instead of so if you go to a previous thing, so basically a normal distribution, so a Gaussian distribution with mean as this term and variance as this term, right, is basically like, if you like look at a proper execute practical way, would be something like this. So we are taking the image, scaling it with the mean, with this term here, and then we are adding some Gaussian normal noise, which is again scaled from this term. Now we're doing the same thing, but now we have two different terms. We have root of alpha t bar, and we have 1 minus alpha t bar. So these two things are different terms. This is a beta term, this is a alpha term. But this alpha term is essentially just derived from the beta term only. So alpha t is basically 1 minus beta t, and then alpha t bar is basically the product summation of alpha s is basically, which is basically this thing only. So you have multiple like these, and you basically just use these terms instead. So this is just some mathematical tips. You're not going to dwell deep into that. It's a bit wonky, I think. But I've put the reference if you want to know how we derived this equation. But it's essentially something similar to some properties of Gaussian distributions that have led us to do this. Basically, the idea is that you can arrive at a sum of Gaussian noises is again a Gaussian noise only. So that's like the basic general property that's actually used to derive this. And we use that to our advantage. As you can see, there is a product summation here, right? We use that to our advantage to basically reformulate the original formula so that we can directly take a image and calculate. So again, we are doing the summing part, but instead of do the summing part or anything, like we are not going to calculate all the 500 bit times. Let's say we want to achieve X 500. We don't need to calculate all the 500 time noisy images. We just have to calculate like the 500 time steps. Yeah, I think someone has a question.
And so essentially changing the normal distribution and standard deviation to
Sorry, your voice is breaking.
already.
It's still breaking. Is it just me or is it breaking?
Yeah, it's breaking actually.
You can send your question by chat, Sudeep.
Okay, in the meantime, I have a question. These alphas are essentially calculated by the model, right?
Yeah, no, alphas are calculated by beta, which is a deterministic schedule, like cosine schedule, or like this is actually the schedule of square root alpha prod, which is based on the beta. So the only thing that is so like nothing is calculated by the model in this case, Vesito.
Okay, but
It's all like a deterministic scheduler.
so we are saying every model follows the same cosine model or whatever. Is it
Yeah, it's up to us. We decide there are actually parameters to decide that, like what kind of function or schedule do you want. But just to give an example, I was just giving linear or quadratic or cosine.
Okay. So basically, you are adding the noise here. That's why it's up to us what kind of noise you have to add. That's what we're. So scheduler is to add the noise, right?
Yeah.
Okay.
Like the first job is to add the noise.
There is more maths which is not shown here, complete derivation. So
yeah, this is not the complete derivation. We just directly arrived at the original end result.
Okay.
Yeah. Because like we don't have like actually time to go through the entire thing. So that's the main reason. Like if we expand it over, like maybe if we have another workshop on diffusion models, then we can actually go a bit deeper in the same topic.
Yeah, fair enough, Bhavesh. Yeah.
But yeah, the point being essentially, regardless of whether you understand the math or not, that's irrelevant. But the point being is that we did some things, we did some mathematical stuff that basically gives us the noisy image at any random time step, given the original image itself, like at time step 0. So the noisy at time step 0 directly. So instead of t-1, so for training, it is much faster because now we don't have to rely on generating the previous time steps to arrive at some given time step. Or you don't have to go in a sequential process. You can do batch processes and multiple things, parallelly execute stuff. Yeah. So so now again, as I told you, like this alpha t value is dependent on beta t, right? So this is basically dependent on the beta t's variance schedule itself and are known and can be pre-computed and everything. So you don't need to like pre-compute it all the time. So you can always pre-compute a bunch of values, let's say all the way till 1000. Let's say our maximum is 1000, right? So you can always compute these alpha t values all the way to 1000 before. So you don't have to always recalculate it every time. And again, as I told you, this is just one way this paper took of the approach to create the noise sampler, but there are multiple ways to do it. Like if you go today to any stable diffusion local deployment, so it will have like a bunch of like 10 schedulers that you could use at inference time. So at inference time, we can like use different kinds of schedulers. Scheduler is basically an algorithm which allows us to remove or add noise, and we can the difference between different schedulers is that some schedulers do it in a much faster way, some schedulers do it in a much slower way. So sometimes we can get the best image in just 50 steps. Sometimes we can just get the best image in just 20 steps, depending on the scheduler. But again, the quality will also be traded off, right? It's not like it's going to be perfect. So it could be anything. So that's why I asked. So we can basically do a bunch of different things with different schedulers. Some will be fast, but some will be good quality. Some will be low quality, but some will be slow, but will be of good quality. So that trade-off will always be there. So this is just one example of a scheduler. And this is basically the schedule thing. The graph here is basically a plot of these parameters. So we have these parameters, right? Square root of things. So the square root alpha prod, and then square root 1 minus alpha prod. So this is basically that. So it's basically that your original image is now this much influenced, and your noise is only this much. So as you improve it, your noise is, let's say, this much, and your original image only this %. So it's not like a 80-20 plus split or anything, but it's rather following this schedule to actually split the image and original image and the noise to and add it together. So yeah, so that's just so that was the scheduler. Now we'll actually go to the training part. So training part, we'll just have some pseudocode. So there's some pseudocode, like it will not directly run anywhere. Just to give an example of how it's like the step-by-step process is done. So we start by defining a noise scheduler. So let's say our time step is set to 1000. So we have like up to 1000 time steps you can train it. And then we have a beta scheduler of squared cos cap v2. So it's basically a cosine function, which is squared, I think. So there are different, any schedule you can follow. This is actually we are using the diffusers library to actually create this stuff. So that's why it's given like a bunch of predefined options. But yeah, nonetheless, now what we'll do is, because there's an unconditional GAN, right? So we'll just take a data loader. We'll get some clean images. So we are only getting clean images. So make note of that. We're getting a batch of clean images. And now what we'll do is we'll sample noise to add to the image. So basically, let's say we have 3 images, which has of black and white and 28 by 28, let's say, of fashion MNIST. So we'll basically use torch.randn, which n stands for normal. And if you remember from our scheduler formula, we were adding normal noise, right? And scaling it up and down using the scheduler. So we'll take some random noise of this shape. So that will basically be a noise. And we'll add and we'll sample some random time step for each image. So we have 3 images. Let's say for the first image, I set the time step as 10. For the second image, it is, let's say 30. And the other image, it is 300 or something. Right. So we'll sample some random integers between 0 and 1000, depending on the batch size. And that will basically give us a random time step for each image. Now what we'll do is we'll add noise to the clean images according to the noise at each time step. So a noise scheduler, this is the time where we'll actually take these images. So our images is x0, right? So now we are going to add the noise at different time steps. So let's say our original was x30, right? So we'll just directly get x30, we'll directly get x50 or x100 or whatever that was, whatever the number of time steps that was sampled randomly, right? So we'll just get a bunch of, so this will basically create like a training set sort of thing like during training itself. So we're like generating our training set for our target input. Like every model needs to have an input and a target label, right? So we're just doing that stuff right now. So we're just creating all of that stuff right now on the fly during training. And then we get the model prediction of the noise. So yeah, we take our model, we put in our noisy images, and as you can notice, we are also putting our time steps to condition the model to so that it knows like at what time step that noise was added. So it knows how much noisy or less noisy an image is, so that it can differentiate between more noisy images and less noisy images. And we basically get a noise prediction. So this noise prediction is actually how much noise was added at each image. And then we just calculate the loss using mean squared error, regular mean squared error, with the noise prediction and our original noise as the target that was added. And yeah, and then we basically get the loss, backward it, and optimize it. So that's the general training procedure. Yeah. So what we are, so as you can see, what essentially with this thing we are doing is our model is trying to predict how much the noise was added, like what was the original noise that was added to the images at different time steps. So this is like the full noisy version, right? So we're trying to predict what's the, like how much, like at every time step we are only adding a little bit of noise, right? We're not adding the whole noise. So we are trying to predict what was the original noise vector or whatever, uh, given that these specific timestamps or whatever. That's what our model is trying to predict. If you have any questions in this, can.
So noise is the Y label, huh? It's a target label.
Yeah, yeah. This is our Y label, and this is our Y.
So you are training a model to take from image to noise, and then you are going to find a way to inverse it.
Yes. So this step was forward diffusion. Not this step. This step was forward diffusion, and now this step we are doing backward diffusion. We're trying to reverse this process of addition by trying to predict what noise was added, so that we can take that noise prediction and remove it.
Simply by subtracting noise prediction, you will get the image.
Yeah, not exactly subtracting. Like the scheduler has its own formula to subtract it, but yes, like on a high level, you can think of it as like adding and subtracting. So here we are adding noise, and here we'll be subtracting noise. But yeah.
Bhavesh, Krishna here again. I
Yeah.
have the same question back again. Now, how do we, if you want to use this model for any image?
Yeah, we'll go to the inference part, right? So there's just the training part.
Okay, so at that time you need to give the info time steps also the input. So how do we,
So
how
our
to
model
decide
is
that?
being so our model is being trained to do noise removal at any given time step, right? So now at actual time, so it is not like we are going to train. So we are not training it separately to go from complete noise to a good image here, right? So we are just training
Right.
it to remove noise at random time steps. So
Right.
we use that. So the model's ability to remove noise at random time steps is going to come at handy for our sampling process. Because now what we'll do in our sampling process, we will iteratively, we'll go from 0 time step to 1 time. So we'll tell that, give me xt minus time step 1. At time step 1, what was the noise
Yeah,
or whatever? We'll
that
do
I
it
got
that
it.
way.
No, that I got it. What I'm saying is, so at the time of inferencing, time
Hmm.
steps also has to be one of the parameters, right? Am I
Yes,
right?
yes. So that time step will be just a regular sequence of 0 to 1,000 or whatever,
Okay,
whatever
so how do
number
you
of time step
decide
is.
that?
No, it's just dependent. In our training, our maximum was 1,000, right? So we can go all the way up to 1,000 to basically generate the perfect image. It's not, it's a trial and error. It's not like there's a hardened rule to follow to find out how much. It's up to us how many steps you want to go through. Whenever you get the clear image, you can stop. If you're, let's say, monitoring the image generation process, and then you say that, okay, this is a good image, let's just stop here or something. You can do that if you want. But generally, obviously, that will be an extra. You'll have to watch over your image generation process to find out at what point it is generating the best image. But you can generally make an estimate based on a few trials and error. In this particular case, this model is trained for like 1,000, right? So you can go to 0 to 1,000.
Or like some other models, can you specify if you go
Yes.
beyond, say, in the last 10 iterations, with the noise, the delta
Yeah.
noise
So
is not significant, then you can stop.
yeah. So stable diffusion at time, usually 50 steps, you get a pretty decent images. At 100 steps, it won't really change the semantic or the semantics of the image, but we'll just maybe add a little bit of more details to the image. But otherwise, the most of the image remains the same. But again, that kind of depends on the initial random noise that you gave it to the model, depending on the seed value. We'll experiment with that in our practical thing when we actually implement the process. Yeah. So yeah, so this was the training, right? So a sampling. So now our model is basically trained to arbitrarily pick up noise from different timestamps. I will take that to our we'll use that to basically go from 0 to 1,000 in a proper step. So we'll like properly go from 0 to 1,000, and we'll do this iteratively. So the model wasn't trained to do it iteratively, but it has the ability to go at any time step, right? So that will anyway, it can be repurposed in whatever we want. So we iteratively, so to get the best images, we will in fact at inference point basically do it in an iterative fashion, so that we can get we can iteratively and slowly and consistently remove noise and get the best image that's possible. So we'll take a sample, so random noise. So this is basically a random noise. We'll randomly sample it. We'll take our model, we'll put our sample into it, put our timestamp t, which is basically our noise scheduler steps, right? We're just enumerating over it, and get a noise prediction. And yeah, get a noise prediction, and then we'll take that noise prediction and give it to the noise scheduler. It will take the noise prediction, the timestamp, and the sample, and it will, and the dot prev sample. Again, this is a reverse forward. So forward diffusion was adding it, right? So we had x0 all the way till x1000. So x1000 is basically our most noisy version. So this is like fully noise. So this is actually this part. This sample is actually this part. So we want to pet the original image, right? So we are going to go backward, right? So that's why we are doing prev sample here to go to find a denoised version, or like remove the noise from it. So a noise scheduler will take the noise prediction, the sample, and the t and everything, and we'll do prev sample to actually remove that noise. And then we get our sample, and then again, now our sample is updated. Now we again go loop it over and over again for all the time steps. And yeah, and then we basically get our original sample without the noise. That's the idea behind it. Yeah. So this is how we are going to sample and like sample new images from random noise in DDPMs.
Very interesting. I'm thinking of a very slick trick. So it's like a painting. So you are destroying the painting, and then you are learning how to retrace your steps. So you have a painting,
Yeah.
you color over it, you destroy it by coloring over it, and you are measuring the amount of destruction you have added. And then when it is completely destroyed and messed up, then you retrace the steps, and it calculates how much reversal it has to do to get back to original.
Yeah.
Yeah, Vivek, one very simple example that I was just thinking, what about a washing machine where you put the clothes in there and you put water and detergent there, the noise there, and then you try to wash it and then dry it to come to the original thing.
Correct.
Does that process, all the processes are similar to that?
Yeah, that's a fair analogy. Yes. So
Because you put in the
it has learned destruction. Now it is
yeah
learning undestruction, going the other way.
yeah yeah. I mean, you put it in the dryer and it cleans it and dries it in iterative fashion, and then finally you get the original class.
No, it learns the destruction and forward step.
Yes, so that is when it is putting in water and detergent and increasing the noise there, and then once it goes into the other, I mean, the number of cycles that it does to go there, and then number of cycles it comes to dry it, clean it, and dry it and give it back.
Yes. Okay.
Yeah, so this was DDPM. This was the general diffusion process. I hope you at least got an idea of what's going on, like a general idea. Now we'll actually go to the main thing, is stable diffusion, which is basically a conditioned diffusion model. So you condition it on text and generate images from text. So that's the goal behind stable diffusion. So stable diffusion is actually based on a paper called latent diffusion models for high quality images. So basically stable diffusion is a variant of something diffusion models. So it's like a variant of normal diffusion models. And stable diffusion, basically the same thing essentially, except that the data set was a bit different. That was not different exactly, but rather a subset of the original paper. Much more quality controlled way than the original paper. So anyway, we'll come to that. So there are a few issues with normal diffusion models that we look right now. normal diffusion models that we had looked right now. So that is for, let's say you're generating at high resolution. So your unit will also have to process high images, right?
हाँ
Right.
वेबिनार है कहीं लेक्चर नहीं
So
हम्म,
yeah, so I think so let's say currently we are generating 228 by 228 pixel images or something. Now if you want to scale it up to 512 images, and then 512 by 512, and then you go to, let's say, 1024 by 1024. So the more quality you want, or the more resolution you want, the more the compute requirements and everything, right? So it scales up drastically, and your process will all become slower and everything, and you cannot run it at your consumer GPUs or anything. Like, it won't be possible to train it at cheap price, or yeah, or forget training, even to run it normally for inference, it would be very expensive to run if you want a really high quality and high resolution images. So to solve this, what this latent diffusion model does is that instead of operating diffusion at the pixel level, we basically do it at the latent space. So what's the latent space? So and then
Bhavesh, sorry, can you repeat that? Why you are saying it costly? I missed that point.
yeah, it's basically like your unit will basically take in larger images, right, as input. Your larger resolution, the larger the resolution your unit is processing, the larger the compute requirements, right? If you want to generate high quality HD images, at least let's say 1024 by 1024 pixels, that's like, your unit will use a lot more memory. Your memory requirements will increase, right? And as your memory requirements increase, your compute, you will also need a much powerful compute if you want to do it in less time or whatever.
Okay.
So our goal is to generate high quality images of high resolution. So normal diffusion models don't do that. Like it's difficult to do that, like at a way that can give you access. Like currently, Stable Diffusion is open source and it can run on your laptop. Like it's so optimized to run like on any device. Like even with the minimum compute requirements, it can even run on Mac. In fact, that has like a bare minimum that it doesn't even have a GPU. It can even run on that. So yeah. So that's the advantage of latent diffusion models, is that so how is it going to do that is basically, instead of doing latent diffusion at pixels, so now instead of operating directly on images for diffusion process, what we'll do is we'll actually use the latent space. So what we'll do is we'll use some kind of encoder decoder to convert images to a compressed representation. So latent space is basically a compressed representation, right? It's a compressed vector. So we'll use another autoencoder actually, which specifically a variational autoencoder we'll use, and we'll actually compress the image to a small latent vector and actually do diffusion on that. So our small latent vector will contain, the diffusion process will contain all the semantics and everything of the image, and our variational autoencoder's job is to take that denoised vector or whatever, the latent vector, denoised latent vector, and upscale it, or like decode it, not upscale it, but like decode it to a high quality image. So the quality control is done by variational autoencoders. The semantics and details of the image, like what needs to be in the image, who is doing what are the objects, what are everything, lighting and everything, that is controlled by the diffusion process. Again, we'll go to a diagram and everything, but yeah. So additionally, the idea is that we can use text conditioning. So we can add text embeddings to the diffusion process in order to condition the generation on text instead of timestamp. Like timestamp will still be there probably, but text conditioning is the main thing actually, is that you add your embeddings, concatenate your text embeddings to the latent vector embeddings. Not exactly concatenate it directly to that, but during the process in the unit, you actually add cross attention to kind of include text prompts conditions as well. And basically, with all of these tricks and everything, Stable Diffusion has achieved basically state-of-the-art results with this technique and can be used on consumer GPUs to generate super high-quality images. The original images that you saw in the slide, right, that were all generated on my local laptop. In fact, these images were all. So yeah, so you can see the quality that we can generate at.
Bhavesh, sorry, Krishna here. One question here. When you say text conditioning, what is that?
You take text to image. Basically, you write a text that I want an image of a tree. Okay. That's a text, and then so our original diffusion model was generating random images, right? Now it will actually only generate image of a tree when you say that you want the image of a tree. So you train it with the text. So it's a image text pair. So you'll have an image, you'll have text, and then you'll use that to basically train the models to generate particular images only of your choosing using text. So it's text to image. The task is text to image basically. So you start and you generate an image. Yeah. So yeah, so the original paper, this latent diffusion models, used the Lion 5B dataset, which is basically a open source data text descriptions or captions or whatever. And Stable Diffusion, what they basically did is they basically created a new subset called Lion Aesthetics. So aesthetics is basically a subset of that. It's not even the 5 billion full data set, but it's rather a more quality controlled data set. So they use some automated methods, so which is basically like clip models. So they use the clip model to filter the data set with only images which were of good quality and which were looking good, like looking great, of good aesthetics. That's the basic idea, is that that when your training data set only consists of good quality images and which look good, not just quality, but like from a resolution point, but like in the semantics, it's like of good quality, like the images are more interesting and better or whatever. So that's the main difference between Stable Diffusion and the original paper that it's based on.
If
Yeah,
you want
so
go from text to image, you have to have something like clip, right? Because clip is
yeah,
the coordination between text to image.
yeah,
Without something
yeah.
like
So
clip, you can't take it from text to image.
like you will see, not without, like basically you need some kind of text encoder. It could be clip, it could be like a BERT model, it could be
Yeah,
anything.
yeah,
Stable
yeah.
Diffusion uses clip. Yeah.
Okay.
See, here the confusion is, on one hand, the objective is to remove the noise, but also we are saying, text to image. That is where I'm getting confused. So what is
Yeah,
the objective?
so our objective is to remove the noise in such a way such that it is aligned to the text, such that it generates what's in the text. So if I say that I want to generate a tree, it will not just remove noise. So generally in normal conditional diffusion models, it's removing noise and generating random objects, right? On the data set only. So our data set, let's say, was of clothes. It is generating a cloth, but it is just a random cloth. Now I want to control that. I want to control that so that I can, instead of generating any random, I want to just generate shoe. So I can give it a condition that, so in the model itself, so that's the job of the model, to learn it in such a way such that when it removes the noise, it actually generates the actual original image that we are intent to actually generate. In our training process, we are just putting random noise and removing some random noise, and it will always give some random image. It's not going to always give us the same shoe image or same pant image or same shirt image. So, but now we are trying to control it. We are trying to condition the unit specifically to basically take the text embeddings, text description or whatever that we want, and incorporated that in its trainings to actually remove the noise. So that we are going to train it in that way such that when it does removes the noise, it takes the text into account.
So here the idea is, fundamentally, what the image probably contains, and you
Yeah.
want to get that. Suppose if
Yeah.
you have a face image, you want the model to give the face. You don't want the model to give some other shoe. Is that the
Yes.
fundamental idea here? Okay.
Yeah.
Okay.
Yeah, we are blending two different models. So one is a noise to image, the other is text to image.
Image.
We
Okay.
are blending them. This was also the principle behind conditional GAN. So in
Yes.
conditional
Yes.
GAN
Exactly.
also we used
Okay.
to generate an image given another image.
Okay. Okay. Yeah. That clarifies. Yeah. Yeah. Thanks. Yeah.
Yeah. So LDMs is basically not a single end-to-end network that is basically doing everything. It's basically like a collection of multiple models. So we have three different main components, I would say, that are at works here. So one is the image compression. Image compression. So as I told you, we're operating at the latent space, right? So we are taking a big image. We are using an encoder to basically turn it into a small latent vector, and basically then doing that our unit. So this is our unit, let's say. So then we are taking this unit to basically generate the right latent representation, and then we'll use the decoder to kind of decode it back to its original image. So now, because we want to do this encoding decoding part, right? So to do this encoding decoding part, we are going to use variational autoencoders. So the original paper actually experimented with two things. It experimented with VQ GAN. So this is the part where it kind of used GAN aspects as well. And then variational autoencoders. Stable diffusions are actually using the variational autoencoder version. So that's why I've just mentioned that here. But yeah, so VAEs are basically trained to like effectively and efficiently. So it's separately trained. It's not trained along with the LDM or anything, but it's separately trained to first effectively compress and efficiently decompress the images from and to and from the latent space. So yeah, so that is that perceptual image compression, which will, the idea is that you train it in such a good way such that your details and quality remains top notch always for things. So that's that. And then we have our, obviously the main actual thing, that is the latent diffusion process. So this diffusion is performed on the latent space to reduce the computational complexity. And this is basically responsible for all the semantics. So semantics of the image, like what, so if you're talking about a tree, let's say I'm talking about a monkey in a tree. So this diffusion process will take care of creating the vector in such a way such that there's a tree and there's a monkey, such that when the decoder of the VAE decompresses the image from the latent space, it will basically generate the right image that we wanted. Yeah. And the third component is basically the conditioning. So in this case, we, at least in stable diffusion case, we use a clip text encoder, which is frozen. So we are not tuning the text on decoder in, we're directly using the pre-trained model as it is. So in general, when we are actually doing the diffusion training, this is pre-trained and this is pre-trained. Both of these are pre-trained models like that we have trained separately. Clip is anyway already available pre-trained, so we didn't like separately train it as such. Although the folks at Stable Diffusion actually created a new clip model also, like now they have like open sourced it, and I think it's called Open Clip. But yeah, that's a different story. But there's also an open source trained version of Clip that was trained on Lion instead of the closed source Clip that was released by OpenAI. Like OpenAI released the models, but it didn't release the training data set or anything, right, of Clip. But yeah, so our clip text trunker will basically encode our text prompt and condition the latent diffusion process with this embedding by concatenating the embeddings here and using cross attention. So in our unit here, now there are a bit more different things. Now there is cross attention and everything, which will take our text prompt. So this is, let's say, our text prompt. It will add concatenate it in different steps in the process, in this process here, and it will add cross attention with this to basically incorporate this text information into this entire diffusion process. So your model is now not diffusion process, not just dependent on the timestamp, but right, it's also heavily dependent on the caption. So our training, so again, we'll look at the training process with some pseudocode to kind of know what's actually going on. So again, we'll start a batch with a batch of images, but also a batch of text, because now this is a text to image task, right? We want to train images with both text and images. We will use, so during the training, only the encoder part is useful for us. So we'll just encode the images to the latent space using our VAE encoder, trained VAE encoder. And we'll then, again, the same thing, we'll sample some noise, we'll sample some random time steps, we'll create some noisy images. So this is actually not noisy images, this is like noisy latent spaces specifically. So a typo there, sorry. Noisy latents. I think I had updated, yeah, okay, yeah. So this is noisy latents. Yeah. Noisy latents. Yeah, never mind. So now we'll take our text. So our text from our text prompt, we'll encode it using the clip text encoder and encode it. And now we'll get a model prediction of the noise prediction based on our noisy latent images actually. So again, typo there, sorry. So based on our noisy latent images, the time steps and the text embeddings, which is like the main thing here. We'll do that. And then finally, we'll then do the regular thing, that is minimize the mean squared error loss of the noise and prediction, backward it and optimize it, etc. So the training process again is kind of is like at a high level, at least it's similar to the one that we did previously. except the only thing now we are incorporating text embeddings and operating at the latent space using our by encoding the images to a latent space using our VAE encoder. So yeah. So that's yeah. So any questions, if you have anything, you can ask.
Good stuff so far.
Okay, so yeah.
But
So that's the
all of these things are not rocket science. We have been doing these things since forever, right? Many years now. So how come Stability AI developed this kind of model and not people like us?
like there's a lot of compute power also involved in here. So they
Is it
use, I
just
think,
compute power? But algorithmically, it's not sciences. We know this stuff.
Like there's a lot of math that goes into deriving the actual stuff. We are just looking at it at a high level here.
Okay.
But yeah, there's a lot of that, and there's a lot of scale as well. So it's a lot of images, like billions of millions and millions. I think 2.5 billion images. I think something, I guess. But yeah, millions and billions of images and a lot of compute power that goes into training all of this.
Fair.
That's the basic idea behind is that it's an open source version too, basically, because normally all this power is usually relies on the it's usually with the big companies only, which have the resources to do it. But yeah, that's the specific thing in here is that we did a similar scale thing, but on an open source level instead. So it was a collective, it was a group thing by multiple companies and researchers and research groups joining together to basically do this. Stability was just, I think, the sponsor for the compute, but otherwise it was done by the computers vision group of University of Munich, I think, from in Germany, if I'm not wrong. And I think people at Runway ML and yeah, and Stability ML also had a few researchers, but Stability was mainly the provider for this thing. Okay. So this was the training process. Now we'll actually look at how the sampling or the inference is done. So now what we'll actually do is we will take again some randomly seeded Gaussian noise. We will directly we'll turn it into latent. So like we are not using the encoder, VAE encoder or anything, because it is just random noise, right? So we'll just directly random a latent vector, sample a latent vector, take our text prompt as well, and then take a conditional latent unit and put this latent vector into our unit, get our noise predictions or whatever, and then use our scheduler algorithm to basically iteratively remove the noise and then feed that back into the model and then basically iteratively remove noise and noise. And while we are also doing that, we'll take this text prompt, we'll take our clip and text encoder and add it to our diffusion process so that it's conditioned. And then finally, after a k amount of steps, we will basically take that final latent vector and put it through a decoder. So during training, we use the encoder part of the variational autoencoder. During inference, we'll use the decoder to basically decompress that latent vector representation to a full-fledged image. Yeah, so this is the inference pipeline that we are actually going to implement right now in the hands-on way.
So you didn't show the training, chart. You are showing the inference chart here.
Training, I showed it in like pseudocode format.
Fair, fine.
Like it was easier to show it in this with, and because chart would actually make it more confusing.
So Dall-E is very similar.
Sorry?
Dall-E 2.
Yeah, Dall-E 2 is similar. It does use diffusion, but it's a bit different though. The process is a bit different. But it still does use diffusion. The architecture is different though. But yeah, it's still like at the end of the day, it still achieves the same thing. So again, it also uses clip and diffusion models unit and everything, but it is slightly different. But still essentially the same. Yeah, so the next thing is we are going to do some hands-on implementation. So we are not going to train a diffusion model from scratch or anything, but we are going to actually implement this pipeline of inference using the raw model. So we'll take a raw unit will take a raw, like pre-trained only, like which are trained, will take our encoder, decoder, unit, and everything, and basically try to implement this pipeline from scratch to get an idea of how the inferences or the sampling is taking place. Yeah. So, okay. So, let me. Yeah. So I want you guys to basically put your CellStrat workspace emails onto the chat, I guess, because we need GPU to this. So I'll actually assign a. So you don't start your workspace. So
So
yeah.
Bhavesh is
So
going to
this.
start your CS Hub instance in GPU mode temporarily. For that, you have to put your email here, I guess, in chat.
Yeah, the account email, whatever your account email
Don't start
address
your
is.
workspace. Bhavesh
Don't
will.
start. Don't click. Yeah, do not click here. I'll just show you how it's in my case how I do. So I don't click on the start button. You just share your email and start. So as you can see, I didn't start it, just turn to pending mode. That's it. That's what you have to do. Yeah, do not start your workspace. Just put your account email address. I think Mirinmoy dot goes Sudeep Goswami. I don't think you have an account because it says that this account doesn't exist. So maybe you'll have to request an account and create an account in CS. So I think I'll go ahead and create that account. You can basically request an account and yeah, or I just put that in the chat and I put that. I think Salim is also not an account, so I guess you okay. I'll just create an account. Yes. You can actually request an account, and in your organization name, when you're requesting an account, just put in your organization as Diffusion Workshop, or just put Diffusion as the organization name. That way, I can filter up the usernames from today. You can change that organization name later on in your settings, but yeah, just for now. Yeah, I think even mail to Jagnesh is also not an account. So I request you guys to sign. Just click on the link here that's shared and request access. So it will be like this. So in your organization name, when you're putting it in, just put diffusion here.
So our upcoming API will be on CellStrat Hub or SageMaker, Bhavesh?
Um, yeah, I think that would be on SageMaker, I guess.
Okay. No, but you are able to do it here in Hub, so why not on Hub?
I think we're just testing it on Hub, the deployment. Yeah, I mean, like we have to build that thing, right? So I'll look into that.
Okay.
So I think Mrinmoy.Goswami, I have done the approval. I think you should have received an email with the username and password. Can log into that. And once you log in, just again put up a message here that you have logged in. And then don't start it. I'll start it from the back end. Yeah, I think the request for Salim.abstract is also approved. So you'll receive an email with your credentials, temporary credentials. I haven't received any new requests so far. Mail to Checkmate. You can also send a request actually. And you have put your email, but your account is not there. So and those who had given, I think Vivek sir and all, your account has in pending or has it started?
Yeah, I have gone to data recovery. That's fine. Let it be.
Okay, so I think whoever had sent their 2 requests, now I have started their workspaces.
Sending my alternate email. If you can start this one in GPU.
Okay.
Hey, Vivek, one question, right? I think my account is now deleted, looks like. Maybe I've not used for a long time. Okay, so I'm not able to access again. It's the same email ID.
So you can sign up again. Bhavesh will create it.
Yeah,
Approve.
I've created the account. You can check your email. You should have gotten the new credentials for the new account.
No, I didn't get any mail on
Achha, no,
Tuesday.
okay,
Ah,
you
yeah.
might have not put your email. Okay, put your email on the chat, I guess.
Okay, I'll just put it. Thanks.
Yeah, Monima will delete accounts after 2 months of
Oh,
inactivity.
okay, no problem. Okay.
You can create again.
Yeah. I'm just. But I tried to sign up, but it's not allowing me to sign up. That's the thing.
You can request access on, yeah. So you can go to the email. I can't log into the provided credentials. Should not be the case.
You can do password reset, Sudeep Goswami.
What does it say? I think it should. I okay. Yes. Yeah. Okay.
So it is saying me, please fill up the fields again. So I have given all the fields. I don't know.
Oh, sorry.
I'm getting, it's saying, fill up the fields again, though I have given all the fields. And
Anyway, your request has
Uh,
come. So, Bhavesh, you can create Monimoy Purka Yast account.
okay.
This Monimoy, there are two Monimoy. So, Bhavesh here on the call.
Yeah. Actually, that two one. Yeah, I'm creating this one that you just said. monimoid@gmail.com.
Gmail, yeah. Yeah, got it. Thanks.
So, Salim and Jay Ganesh as well.
Uh, Sometimes you can do, if you're not able with that thing, you can try using the forward password and reset your password, like whatever of your choosing. And I have started the workspaces for Sudeep Goswami and Jagnesh. You should be able to see at least it in pending state or running state or whatever. Yeah. But nonetheless, I'll share the notebook email that we're going to basically use today. So you can download the notebook from here, and yeah, you can run it in. Just download the notebook, I guess. And basically, once it is started and everything, you have to basically click on launch Jupyter Lab and then open up, and it will basically open up a Jupyter Lab instance.
Bhavesh, you have shared a shareable notebook. I mean, it is downloadable notebook, huh?
Yeah.
So from CellStrat Hub, we can just share this link. People can download it.
No, this is just a normal link to download. It's just normal. You just download. You just open that up in your browser, download the notebook, and then upload it to CellStrat Hub. So you can upload the file from this upload button once you open it. So you'll see a button called Upload Files. So just click on that and upload the downloaded notebook. Yeah, you can basically actually run those things. I'll just go and explain the stuff, the code here basically. Meanwhile, people are preparing. So yeah, so this is basically from scratch. So the first thing that you have to actually do is you have to basically download the model files. So we are going to download the model files by using the terminal. So I think on the free tier, so even I am specifically for this workshop on the free tier, is that you only have like let's say 1 GB of storage, but you do have root storage of about 80 GB, I think, of which 15 GB is usually free. So what you have to do is you have to actually click on this big blue button called, this is called a launcher. And on the bottom, you will see a terminal option here. So just click on that and basically copy these commands. So one is ceding to the home directory.
I can't run it in the book itself.
You can, but then the paths will actually change a bit. Actually, running it
Okay.
directly in notebook would mess up the path. Like you can, I guess, but yeah, then you'll have to just run it in this way, I guess. Download it up, and then again seeding back to this way. I think this way you can run it in the notebook if you want. But nonetheless, like you can just run this command in notebook, but put an exclamation mark. But after the commands again, no, actually the cd thing directly with exclamation mark, this does mess up a few things. So yeah, so just download the model file, and this will download the model file in a minute, I guess. It's basically not a single model file, but rather a bunch of model files. So the way the extracted zip file would look like once it's done is that you will have a Stable Diffusion 1v14, I think, notebook, not explicitly just v14. And you would have some feature extractor. You would have a scheduler, config, you'll have text encoder, which is basically a clip encoder. You will have a clip tokenizer, we'll have our unit, and we'll have our VAE. So these will basically be components, and all of them will have their own different models. Yeah. So also, meanwhile, make sure your notebook is in PyTorch 1.9 if it's not this kernel. And then we basically install the diffusers library. So we are going to use a library called diffusers, which is basically our library for diffusion. So similar to transformers, this is like specifically for diffusion. So yeah, again from Hugging Face, I guess. Yeah. So we'll pip install diffusers, and we'll also update a bunch of other libraries like Torch and everything if needed. Yeah, so I think in my end, the extracted files, the files have been extracted. So I can just do ls to just check the folder that it's, yeah, I can see the folder here. Okay. And I think PyTorch is updating this. So let's wait for that.
So we should run pip diffuse that notebook line. Pip install diffusers.
Yeah. The pip install diffusers and the other pip installs.
So not import torch yet.
No, yeah, like install it. We need an updated version of the PyTorch for this, so we'll update Torch and a few other libraries.
But sorry for interruption. So the first few lines,
Yeah.
right, CD and wget, that is to be done in the terminal only, right?
Yeah, that have to be done in the terminal.
Terminal. How to go to the terminal? Can you show me it again? Sorry.
You can click on this blue button on the left. This will open up this launcher, and you'll see a terminal option here.
Okay. Okay. Thanks.
So yeah, so once your libraries have been installed, you can then run the cells probably. So I'll just go over the code. So yeah, so we are going to first load a few things. So first thing is that we are going to load the variational autoencoder model, which we'll actually use to decode the image, decode the latent vector that was diffused to let us denoised to a proper image. So because we saved, so this is the path where we, like if you follow the previous step, you will have your folder VAE model files in this particular folder. Then we also load the tokenizer and text encoder, so which is basically clip tokenizers and clip text models. So we'll do that same thing, and then we'll also load our UNet.
No, it's saying we have to restart the kernel to use the newly installed.
You don't really need to. It says may need to. The reason being that we have not run. If you have not run the import torch step right now, then you don't need to. If you went like in a sequence, then you wouldn't have to.
Okay.
The reason is that if you already imported it, then to update the imported version, you would have to restart it. But because we didn't import it yet in the first two cells, you don't need to. You can just directly run this cell, then run the next cell. You can actually kind of run the entire notebook if you want with the run option and run all cells. Not run all cells, but run selected cell and all below. Meanwhile, so yeah. So we load these things, and then we will also define our scheduler. So we are going to use a LMS scheduler, LMS discrete scheduler, and have some parameters for it, some beta, start beta, and some scaled linear schedule, and the number of train steps that is 1,000. So again, in diffusion, the train steps are total, like up to total 1,000 train steps are there. And yeah, we can do that. So just run that cell as well. We'll just move the models to GPU. And then we'll actually define our actual stuff, things like our prompt. So we have our prompt here, which is a concept scene watercolor painting of a Demiric temple. So our prompt can be, so it's a bit of prompt engineering that we have to do, but in this case, for stable diffusion, we add extra keywords like 8K, integrate details, ultra high resolution, cinematic lighting, things like extra keywords to basically make the image much better and increase the resolution, the quality of the image, basically. So there are a lot of tricks and tips for how to prompt your stable diffusion models. Like that's going to take another thing if you want to do that. But yeah, in general, you can Google up a lot and you will find a lot of resources to do the right prompting. But the idea is that we are mainly trying to create an image of a dimly lit temple, a watercolor painting in a scene or whatever. Then we set our height and our width. We set our number of inference step, which is the number of denoising steps that we're going to take. So we set it to 100. 50 also works, but we'll try 100, we'll try 50 and see what works and what doesn't. Guidance scale is something like, actually, I'll get to that. I'll give you a gist when we get to the guidance scale part. But for now, just think of it as basically lower the value, the more less diverse it is, the higher the value, the more accurate to the prompt it is. Yeah, so so in that way, you can think of it as the less the value, the less closer it is to the prompt. The more you want it to accurate to the prompt, you increase the guidance scale. But sometimes sometimes too much guidance scale kind of destroys the quality of the image. Like it is accurate, but it's not looking good or aesthetically visually appealing. So depending on that, we try to put a good value. Like we'll have to, again, it's a trial and error thing. You cannot get the best image in the first try itself. this is a trial and tested thing. So that's why I specifically put 12 and a manual seed of this. This is actually from a different image that I previously generated. So I set those seeds here. Again, we are going to randomly generate a noise, right? So to control the randomness, we can set seeds, which are, if you are aware of random number generators, they always use some kind of seed to generate the number, right? And to basically deterministically create the images so that we can always achieve the same images with the same parameters, even though there's randomness. So yeah. So yeah, so these are some parameters that we just defined. Then we'll just take our tokenizer, tokenize the text, and create our text embeddings. And yeah, so that we'll do. And now we'll actually do something called unconditioned text embedding sort of thing. The idea here, okay, so I'll just first tell what it is, then I'll tell you why it is. So is that there is something called classifier free guidance in this models, which is again a different topic. There's a different paper on it. Stable diffusion people use this, but due to short of time, we couldn't go over that. But the general idea is that to have a balance of diversity and accuracy to the conditional prompt or whatever that we are using, in this case text, to have accuracy to the text prompt, as well as have some diversity and creative freedom, we generate our images which is like a hybrid of a conditional generation and a conditional generation. So a conditional generation is the one which has text embeddings embedded into it, like using cross attention, and the unconditional one is without the text embedding. So we actually generate two images, two denoised versions. One is which is unconditional, one is which is conditioned, and we used and we like mix it in such a way such that there's a good balance of creative freedom and diversity while staying accurate to the prompt. So it's not we are directly purely using a prompt. So classifier free guidance is basically that balance. So the scale that we just set basically determines how close do we want it to go to the prompt, or how far do we want to go it from away from the prompt. So this scale will basically do that. So to do that, we want to, because our model will take in dummy, our model will take in fixed length inputs or whatever, right? So we'll also, for unconditional generation, we'll also put some dummy text. So dummy text is basically the pad token. So we'll just pad empty tokens and create another text embedding, which is of the same shape and length as the original text embedding, but it doesn't have any meaning. So this thing doesn't have any semantic meaning or anything, while this has our semantic meaning of a text prompt. So that's why we just do this. And then we basically create our total text embeddings by concatenating the conditioned embeddings and the original text embeddings. This will basically give our final text vector, which has both unconditioned attributes as well as text conditioned attributes. Now this is the part where we actually do the generate some random noise. So again, to control this randomness, we had set this manual seed, right? So that's why we are passing also in a random n function. We're passing a generator here, the random seed thing, and we basically generate these latents. And as you can see, our latents, depending on our size, are scaled by are reduced by a factor of 8. So we are going to basically run our diffusion process in a pixel space of 64 by, not exactly pixel space, but a latent space of 64 by 64 height and width and 4 channels. So as you can see, it's really efficient in terms of computational complexity, because now instead of working at 512 by 512, we are just by a factor of 8, we have reduced our total complexity of the processing that we need to do in the diffusion process. We'll use the autoencoder to basically then again turn this vector back to our original image. So yeah, so we do this. Now we set our timestamps as the number of inference steps. So we set our timestamps to 100, right? So 100 steps we'll be using our scheduler to denoise it. And then this is some scaling that we are just doing. So similar to how we pre-process our images, right, with normalization. It's similar to something similar to that. We are just scaling, the scheduler has some parameters to which we are scaling our latents. And now this is the actual denoising loop. So the first thing is, again, we have two text embeddings here, right? If you notice, we had our unconditional embeddings and our text embeddings. So to account, so So like to basically have latent embeddings for both the situations, because we're doing twice. It's kind of like we're doing diffusion twice, one with condition and one without condition. We'll just expand our latents into 2. So that's why we're just doing multiplied by 2, because you want to generate 2 images sort of thing. Yeah, so we like in a single forward pass we want to do it. Otherwise you can do it twice also, that's the same thing. But yeah, nonetheless we take our latent model input and we again scale it using the timestamp, using the scheduler. It has some scaling properties to normalize it and everything. Then we predict the noise level. This is the actual part where we take our unit, put in our model latent model input, the timestamp, the text embeddings, and then we do dot sample to basically get a noise prediction. Now, because we are doing it 2 times, right? So our noise prediction will basically contain the unconditioned noise prediction as well as the conditioned noise prediction based on the text. So this will basically, so because we are trying to create a good balance between diversity and text prompt accuracy, right? And that's where our final noise prediction is basically going to be noise prediction unconditioned plus the guidance scaled multiplied by the noise prediction text minus this thing. So this is basically like this is our basically a main formula to adjust our to do classifier free guidance. So this is called classifier free guidance, which will basically we will use our guidance scale. So we had set this to 12, right? So again, it depends on image to image. You can change it to 7.5. Usually 7.5 is like the average number for most images that you would find in Stable Diffusion. But yeah, so you get a final noise prediction. Then we'll use our scheduler to remove the noise. So we'll take a noise prediction, the timestamp and the latents, and then we'll get our updated latents. And then this loop will again go on for 100 steps and we'll get our final sample. So you can just run this. And yeah, you can see it takes about 40, for 100 steps, it would take about 40 seconds. Not 40, actually 30 seconds it usually does. Just
Wait, this is the same as pseudocode you showed in PPT, right? Basically.
Yeah, essentially similar to that. Yeah. Yeah, kind of. Yeah. And yeah, so once it is generated, we'll again do some scaling with the latents just so our final image is a bit proper. So again, these are like trial and tested hyperparameter tuned values, not exactly specific, not specifically like derived or anything. And then we just basically use our variational autoencoder to decode our denoise latent space into an image. And then we display that image. Yeah. So you can see a beautiful painting of a temple. You can see the quality and everything, like the details and everything. It's pretty good, I would say. So again, now also, if you want to experiment, you can now maybe change the number of inference steps to 50 and see what happens. And see like how the number of inference steps changes stuff. So most likely we'll get the similar image, but it will have a bit of less number of details, or maybe the color will be slightly different than the previous one. So because at the more the number of steps, it's going to still continue refining it. Now, obviously, it's not that always refining it for that much long is better. But yeah, as a general rule, like it's what usually refine it. So it's kind of similar, but you can see it's a bit lighter in terms. I think the previous image was a bit darker. It had more red shade, I think, in the background of the sky and everything. But yeah, so you can also experiment with the prop. You can change maybe height and width. So maybe let's say I'll do it as.
Bhavesh, one thing which is bothering me is all of us are getting similar image.
Yeah, because we set the manual seed here, right? We'll get similar. This is what deterministic output. Because we set the manual, you can again. So if you change the manual seed, so even without changing the manual seed, actually, I changed the height and width to now just to width to 640. And now if we generate it, if you want completely random image every time, what you can actually do is you can just comment out this generator, and it will actually kind of generate. This will always be a random image because now, but the problem with that is that you cannot now. Usually, what we in practice physically do is we actually use another random number generator to generate this random number that you're seeing here, right? basically do that, so that we always know that when we are making our predictions, what were the original parameters, so that we can reproduce those creations or share those parameters with others so they can recreate those creations or whatever. So that's the reason that we use seeds. So these are like the main things that we use in our parameters to it's like there are inference parameters which basically define what our model would look like. And also this beta start and beta end as well. So you can actually update these values as well to get different values, to get different images. So now, as you can see, once I increased the width, my image completely changed. So because now my latent space was completely different, right? Now my latent space was 64 by 80 in length. It was completely different in length. So as you can see this, now my image is like this. Now I can do the same thing. Okay, now I can just do 512 and change the seed to maybe this. So I just removed a number, like remove half of the number and regenerate the image.
Bhavesh, when we launch this as API, which we are working on currently, right? So we
Yeah.
want to give some of these control mechanisms to the user.
Yeah, those control mechanisms will be there.
So user can play with some of the, not too many, so to confuse them, but just a few of the seeding parameters so they can change the paradigm periodically.
Yeah. So now, as you can see, with the different seed, I got a different image. And yeah, and so on. So yeah, so this is basically the main thing. So is that because you're again, also actually I didn't the seed didn't actually do anything. I actually commented it out. So now if I rerun the same thing, I'll actually get different image again, even without changing the seed, because like it's not really affecting the latent generation here.
So we got text to image. So will we probably see text to video, Bhavesh, in near future?
Yeah, I think we may
Maybe
someday. I
that
think
will be the next
there are
thing.
models.
Text
Yeah, I
to
think
video.
text to video is already there. So not already there, but as in like just after these diffusion models, people at Meta and all, they kind of released papers on text to video as well. I think it's called Make a Video, and the folks from Google released a paper called ImageGen Video. And there are a bunch of others as well, but I don't think there's an open source model yet for those models. But yeah, we get that also.
Yeah.
Okay. So, but with these diffusion models itself, you can actually do a bunch of things. So one thing is that what you can actually do is you can use you can use your variational autoencoder. You can take a sample image. Just let's say take some other reference image and encode it using the variational autoencoder to a latent space. Now, instead of using a random latent vector here, I can actually use that latent space as my starting point and do the diffusion process and actually modify that reference image into something similar or different depending on my text prompt. So you can actually do image to image as well with this. You can take an image, edit an existing image, or use that as reference to generate new images with these tricks. So there's a lot of different tricks that you can do with these diffusion models. So this is one trick that you can turn this into an image to image application as well by using more like text to image only, but like with using image as another reference for your generation process or for editing. And you can do also other things like you can do in painting and out painting. In painting is when you take an image and you erase some part of it, and then you tell the model to fill in the gap. So now it will create like a mask sort of thing, and basically when it's doing the diffusion process, it will only modify the parts which were erased and diffuse only those parts, and so on.
But you need to customize the code for in painting, right?
Yeah, but we don't need to train the model as such. That's the beauty of it. Diffusion models is that because all of these parts are modular. We have unit, we have separate latents, we have separate variation autoencoders, we have separate text embedders, or we can always plug and play different stuff to create different things. And the AI community has done actually a lot of stuff. So I think I'll share the next step slide to show you some I think yeah. So you can do image to image generation in painting. Out painting is when you take an image and you do erase, like you kind of extend that image and continue the image to create like a long form, like a long image. So instead of generating a full image in a one shot, you actually step by step generate. Let's say you got an image, but as you notice, right, if I change the width, the image also changes, but I don't want to change the semantics. Like let's say I got a good image in 512 by 512, but I want to extend that image and make it like a full wallpaper or whatever. Then I can do out painting. And now all the actually another thing is that all the images that you saw in this slide here were actually not the raw outputs from Stable Diffusion, but I also upscaled them using a few GANs like ESR GANs, I think. Yeah, ESR GAN, and to upscale it to double or four times the resolution and add some more detail. And also there are faces like this dog face, this human face, and this Elon Musk face is there, right? So these faces sometimes get wonky when we like they're like sometimes the eyes are not that accurate or it's a bit weird or whatever. So there are GANs to actually fix faces as well. So I use those GANs as well to fix that. So it's like like the entire pipeline of a proper Stable Diffusion in production also has upscalers and face fixing GANs and everything as well, to kind of create like a full-fledged pipeline of multiple things working to create the best possible image. And there is this repo called Automatic 111 Stable Diffusion Web UI. I think I can show that repo to give you an idea of what all things are possible. So this is basically like a local thing. I guess you can run it on, I think they do have Colab as well as local thing. And I think this can be done on Hub also. I don't know, I tried it. But basically you can do, it has a lot of extra features built on top of Stable Diffusion. So it has in-painting, out-painting, there is color sketching, there is upscaling, and everything is anyway there. You can also do attention specific. So you can modify the attention in your text prompts to focus more. So you can use things like these brackets to say that focus more on the tuxedo. So you can control what influences your prompt, right? You can do that as well. And you can do textual inversion. You can textual inversion, basically you can use your own custom images to fine tune your stable. If all the textual inversion isn't that accurate, the better way would be the new Dream Booth algorithm from Google. I think that we'll have a workshop on that as well someday. But yeah, so GFV GAN is the one that fixes faces, and real ESR GAN is the one that's for upscaling. So yeah, I think it has so this is like a web UI sort of thing to basically, so it has like a web UI with a lot of settings, like a bunch, like really lot of settings and different things from the community. So the community has innovated a lot on this open source model to create new features and everything. And yeah, so as you can see, the sampling methods, we did the LMS sampler, but you can see there are so many different samplers that we can use. There's Euler A, Euler LMS, DDPM, fast. There are multiple variants of the same things, and so and so. So yeah, so there's a lot of things that you can actually do. So in this.
Bhavesh, when we launch our API on CellStrat app for this, we should give some options, but not too many technical options.
Yeah, obviously.
Because we are targeting it to a business user who's non-tech. So
yeah,
so we should give many capabilities, but for a business user.
Yeah.
So it will not be just one AI app for us. It will be a portfolio of AI apps, right?
Yeah. So, yeah. So I guess, yeah, you can basically see this is like how you mask content. So you basically mask a certain part to do in painting and only add later noise to that and do things like in painting and everything. To, let's say you remember that, and you can say that add a tree here or add a different tree here or things like that. And you can update stuff, and you can take this color sketch, and I think image to image is that you can also draw a sketch with your hand and turn it into a proper image. And you can do scaling and a lot of other stuff is there basically. It's my plot, and yeah, you can see, there are a bunch of features. I think textual inversion, you can train your custom images. You can draw something and get a high resolution version of that, so and so. And there's also seed resize, basically because when you resize it, the image was changing completely, right? So you can actually control that with the seed resize technique to so that when we resize it, the semantics kind sort of remain the same, even when we change the width. But yeah, that's the basic thing about. So today this was just an introduction to diffusions. There's a lot of different stuff. So even after training, so you can do a lot of stuff on top of it to kind of make it better and use different tricks. Yeah, I think that's
this
it. I guess you can, yeah.
area as big as GANs, so GAN was a whole portfolio
Yeah.
of algos. So here there are quite a few possibilities of lots of image related applications.
Yeah. So yeah, so I hope you are all able to run the notebook. So you can also like run the notebook and experiment and tweak it a bit even after the workshop. It's kind of fun to play with. You can change the prompt. You can use your own prompts and try it out. So, like you can maybe generate a dog cyborg or something. You can even try surreal things. You can add realistic things like a tree or sky or a scenery or something. But those things are usually accurate. You can try other fun things as well and so on. So, yeah, overall it should be an interesting thing to explore. And yeah, you can actually try the image to image thing directly itself. We can just use the variational encode function. So va.decode was there. And I think I'll share the tab. So we use the VA decode, right? So similar, there's a VA.encode as well. You can use your image as to encode it into a latent space and use that as your latent vector. So don't use the random latent vector, but rather use your image's latent vector as the starting point. And you can modify your image and try it out and experiment and see what works and what doesn't. You can play around with even the beta schedule values here. And yeah, so I guess that's it basically. If you have any other questions or anything, can ask.
Have you tried image to image here?
Not in this notebook though. But if you want, I guess I can give it a shot. Let's see. Let me save some image, I guess. Let me get an image.
So Bhavesh, one question, right? Okay. So this diffusion model, right? So if I use ordinary GANs and things, it takes long time to get any kind of good image and things, right? But diffusion takes a very short cycle, right?
Yeah. So actually, like time-wise, GAN would do it in a single step. Diffusion does multiple steps. But the main differentiation factor on why GAN diffusions are better than GAN is that GAN is very difficult to train and perfect. It has a lot of hyperparameter. It's unstable. It has a lot of unstable training. It doesn't always give you the best results when you have trained it. You need to do a lot of hyperparameter tuning and all. While stable diffusion is it's a bit simpler than GAN and it has much stable training. So it ends up being better. And also a bit faster because it's operating at the latent space instead of the full pixel level.
Because in the GAN, right, if I train for a few days also, I do not see good quality image coming up.
Yeah. But even these stable diffusion models are trained for multiple days, like on large clusters. I think it was trained on about 2000 GPUs or something, 2800 GPUs or something, on a very large scale of millions of images. But once trained, it can actually do a lot of things. And you can
your notebook is for inference only, right? Not for training.
Yeah,
right?
for inference, yeah. I think I'll have.
Okay, any other questions, folks? So very interesting stuff. Audience, any other questions? Really amazing and cutting edge stuff.
Yeah, there's a lot of, you can actually go to that automatic representation maybe. And there are even actually versions for direct users, which are like applications to just download to your computer and use Stable Diffusion, but they don't have a lot of settings or anything. But I guess the best way to explore would be still with code. So, yeah. But yeah, I guess that's it.
So Bhavesh, we done?
Yeah, I think we are done. Yeah, I was just doing that image to image thing, but yeah, otherwise.
Any other questions, audience? Okay, so thank you all for joining. And let's
Yeah.
keep up the cutting edge work. Thanks, Bhavesh. Excellent session.
Yeah. I think I'll have to pre-process it also to encode it. Yeah, but yeah, you can try that.
Yeah.